Hello everyone, my name is Ivana Tomic, and I'm really happy that we have more time than it was allocated, so hopefully we will again have a nice discussion after my presentation. But again, I know that you are probably all hungry at this point, so I have a very difficult task of keeping your attention. So before I start, I just wanted to give you a few information about what our group does. So our work is mainly focused on producing decentralized and distributed algorithms, protocols that can be used in wireless sensor networks. All our projects are very practical and industry-oriented. So for example, we are looking into security issues of IoT and critical infrastructure systems, into mechanisms for detecting anomalies, energy-neutral operations, so all these different aspects that are relevant to wireless sensor networks. Here I just gave few pictures. I don't know how much you can see, but that's our deployment in one of the wineries in UK, very close to London. The material I will present today was developed during the Petros project that's now in final stages, and that's the project I'm working on, where we are looking into security of mainly wireless sensor networks, but also IoT. I will just give you a brief overview, like what motivated our work, how we developed solution, and then I will give some additional information where I will ask for some contribution from your side. We know that there is a big tendency of making all the cities smarter to improve the quality of our lives, make our lives easier, etc. There are examples of already existing cities. I would start with Smart Santander, which is a small city in Spain that is fully IoT equipped. So it started as a part of the project, and then government supported their initiative. So it's still going on, and they have very nice results. So if anyone is really interested in how they did their work, I would suggest you to look into it. There are also some other examples, but all of this from cities is slowly being transferred to cyber-physical systems and to critical infrastructure, such as water and waste distribution systems, electrical grids, transportation systems. So by using all of these intelligent technologies, we are trying to connect cyber and physical world. And this is where the wireless sensor networks play the main part. These networks, they consist of large number of sensor nodes that sense the environment, but also can provide actuation and amend that environment accordingly. All this looks very, very nice, but there is also a huge concern coming from security perspective, and I'm sure that all of you saw how many attacks happened only in the last year, not talking about anything before. So there is a huge need for developing a system to protect IoT and to provide some regulation and guidances on how to do it properly. An example of system that we are looking at could be water infrastructure system, where we have a large number of sensor nodes that are sensing the environment and then sending this information to the edge or the cloud. And then, for example, by monitoring demand in the water network, they can adjust the, for example, valves to provide enough water to supply some area. We have two projects now that are looking into these issues. One is done with NEC and the other one is Anglia Water. So they're really interested in deploying wireless infrastructure there, as valves are, for example, they're putting them in really not easily accessible places. So it would make their life easier if they can detect easier bursts, leaks, if they can control demand, and then avoid building unnecessary infrastructure if we have smart prediction of the consumption. That concept extended the list of security requirements that we had in traditional networks. So traditionally, we wanted to have integrity, confidentiality, and authentication. Now, because of these complex interactions between cyber and physical world, this list extends, and it goes longer and longer. And what makes it worse is that these are really tiny devices that are constrained from the perspective of resources, and they are physically exposed. So usually they're easily accessible, and anyone can reach it. For example, if they're placed in the park or around the city, you can get in hold of one of these devices. So when we started this work, we tried sort of to identify all the threats with respect to the layered infrastructure of wireless sensor networks. And we ended up with a huge list of the attacks that's constantly growing. The only thing we could say for sure is that they can be internal or external, but this list grows from day to day, and we constantly have cat-mouse game. So once we sort out something, the new threat shows up. So we are constantly being behind. I won't go through each of the attacks. I will just show you examples from each of the category. So for example, well, no external attack is jamming attack, where we have unintentional radio transmission, intentional radio transmission aimed to your device. So for example, if we have industrial system where you have feedback loop, jammer can destroy either your control signal, or it can also destroy your measurements that you are sending to recalculate new control signal, which is more nasty version of the attack. And jamming is usually aimed into physical layer, but there are more smart or sophisticated jammers that can also interfere with your MAC layer. Here are two examples of internal attacks. The first one is selective forwarding, where node can fail to pass your data further. So that causes data loss. It increases delay, end-to-end delay within your network. The other one is wormhole attack, where you can have two attackers and sort of tunnel between them. So all data that one of them receives is passed to the other and vice versa. For example, nodes 7 and 12 are not neighbors, but they get that impression that they are close to each other. So the optimality in choosing the routes is lost. If you look into the literature, there's been a lot of work on building security protocols. But what's the problem is that Then we proposed a solution, and this solution was implemented first in the simulation software and then on the test bed. So I will just go quickly through the steps, and then if you get any questions, you can ask me. I really tried to keep it as light and as brave as I could. By looking into what's available there, we opted to use Contiki sensors, and Contiki provides an open source operating system that was built for IoT. So this system supports the typical IoT stack, and it also has the network simulator, which is called Kuja, and for our purposes, it seemed to fit well. I have a short video, and I hope it will work, just to show you how Kuja simulator looks like. I don't know how much it will be visible, but this is environment, so it can be run on Linux system or within the virtual machine environment. You can set up different network parameters like a grid to have the radio traffic visible. It's really user-friendly as a software, and there is a big choice of modes or nodes that you can add. In this example, I have one sink node and 6 senders that are sending data to the sink. So this is the sync node, and they support different, so you can run IPv6 onto nodes or RIME stacks, so there is an option for both depending on what you want to simulate. And then once you start the network, they have really nice tool that collects the data and provides this data in visual form. It's called Collect View, and you can see how network topology changes over the time, and then you can track how much data has been sent successfully, how much has been received per node or per network. You can monitor temperature of the nodes, their battery level, number of neighbors of each node, which really matters if you have large-scale network. All of this is given in form of graphs, but there is also the table that collects this data real time. What is good about Kuja is that it's simulator but also emulator. So you can try out your hardware before putting the code onto it and really going outside and putting the real deployment. That's it. So once we found simulator, we got to the next problem. There wasn't security module. So none of the attacks were built in. You couldn't test your security measures. So once you built it, what you're gonna do with it? So we started implementing attacks. So far, we implemented 6 internal attacks. And this will be publicly available, I think, probably next month. We tested for each of the attack what's happening with respect to the network performance, how much data loss increases, what's happening with end-to-end delay. And these results here were done on the network of 100 nodes. And what we realized through the simulation was that each of the attacks has its own signature. So either it reduces packet delivery ratio, what's happening with end-to-end delays. So we could roughly categorize them into 2 different groups with respect to these 2 metrics. Then the next step was to provide solution. Our solution is called Antilizer. And it has 2 main parts. So in the first part, we started from the fact that each node trusts only itself. And by observing its neighborhood and different metrics from the network, each node decides where to route data. In this way, if there is the attacker that behaves maliciously, for example, it doesn't pass data, we can observe that and say, I won't pass my data there, I will go somewhere else, and then you will avoid the affected areas. The next problem we have was, okay, we avoid the areas, but how do we fix it, or how do we know what exactly is happening? So on the top of that, we put the agent-based system that consists of, we call them ants, that move around the network. Because the solution is distributed, ants, they carry different information from nodes to node, and that improves the global view of the network. So you avoid so-called hidden node problem, that you don't know, for example, what's happening at the other side for the nodes that are not your neighbors. Each of these small, tiny agents is trained by reinforced learning techniques to be able to detect the attacks. As I said before, each of them had a signature. So if you can train the agent to recognize this signature, it will be able as it moves through the network. Once the attack is detected, this information is sent to the base station, but this is something that will be further improved. It's been just like less than a year that we are working on this. We are now in the final stages of testing the solution. So we are using the large-scale testbed Phyto IoT in France, which has almost 3,000 nodes, and it's really good for testing different kind of topologies. They offer different environments, as they have nodes in 6 different cities in France, and I think now also in Germany they extended it a bit. After this part has been done, we are planning to deploy a single small study in Queen Elizabeth Olympic Park, as we already have nodes that are part of different projects out there. So it would be nice to test it there, as we could test different technologies such as LoRa. This is all that I prepared from the perspective of my work. The last thing is just like to let you know that we have a workshop as a part of Census this year, where we call for papers that would report failures. So if anyone tried to do IoT deployment and had things that failed, or went wrong, we want to hear this because we think that this would be the way to learn from other people's mistakes and failures. So far we had really a big interest. So if you know anyone or you have some experience in putting deployments out, just like let us know. Deadline for papers is mid of August, so there is still enough time. These are the references that I used when preparing the talk, so if you have any questions, I will be ready to take them.
Thank you. Any questions? Anyone wanted to speed up the discussion? Yes, Marco.
Thank you, Marco Ruip, NCC. Sounds like a really interesting conference. I think it's building a bit on where Daniel went yesterday during the IoT panel as well, and sort of call out the errors, call out the failures for others to learn from. I wonder, would you accept a submission that considers the continued use of IPv4 in IoT a failure model?
I'm not sure, but that's something that we could discuss.
Okay.
I can check that for you. So I'm not directly in the organization, but the people from my group are. So we can discuss that further.
Okay, thank you.
Now, counter question. For Marco, why do you think that IPv4 is evil for Internet of Things and IPv6 is safer? Isn't it just a matter of time that attackers will master IPv6 and use it for attacks?
Oh, that's not where I'm going to. The failure mode is simply the impossibility to grow it. It's a scaling problem. I'm not addressing security. It's a scaling failure.
Okay.